So there is one last section in chapter 9. We, however, are going to skip it. That section is all about reactions in aqueous conditions, which is basically more in-depth on double replacements. Instead of doing more in-depth for double replacements, we are going to move into chapter 10. And chapter 10 is a very, very important chapter. The mole. The mole. Yes, the mole is a burrowing animal, but that's not what we're going to talk about in chemistry. Okay? I guess moles can also be discolorations on the skin, but anyway, still not chemistry. In chemistry, when we talk about the mole, we're talking about how much of some specific matter we have. The mole is a unit of measurement. And to be completely honest, this concept does give some people some trouble. Okay? But it's one of those concepts where once you figure it out, it makes a ton of sense. Okay? So let's start by giving you some examples of things that you are familiar with. Okay? So if you have 1 dozen eggs, how many individual eggs do you have? 12. All right. That happens. So what if you have 2 dozen eggs? 24. 24. 3 dozen eggs? 36. Okay? That makes sense to you, right? Okay? We're using the dozen as a measurement. Say how many dozen eggs you have. If you have 1 pair of socks, how many individual socks do you have? 2. If you have 5 pairs of socks, how many individual socks do you have? 10. 5. So that makes sense too, right? Okay. A pair is 2 things. Okay. This one maybe you're not as familiar with. 1 ream of paper. How many individual sheets of paper are in 1 ream? You know? $500. So if you were to go to the store and buy a package of computer paper, we call that a ream, that has 500 sheets in it. So if you had 3 reams of paper, how many individual sheets do you have? 1,500. Okay. See? You know this. Okay? This makes sense to you. However, for some reason, whenever we start talking about moles, some people say that's chemistry and I don't get it. Okay? But it's exactly the same concept. Okay? In 1 mole of anything, we can use a mole to calculate anything. We have 6.022 1, 3, 6, 7 times 10 to the 23rd pieces of whatever. Now, to be completely honest, this number last year was updated. So they changed, let me, should have looked this up earlier. What's the new definition of mole? Now, the official, and this will be in all the new textbooks that are printed since then, it is, so everything is the same, 6.0221, and then it goes 4076. But yes, we never go past that. And in fact, a lot of times in your book, it stops right there. Okay? So that new definition makes no difference to us. Okay? Usually, when we are talking about a mole, we're going to say 6.022 times 10 to the 23rd. And if you notice, that number is right there for you on the test. Now, by the time you finish this class, I imagine you will have that number memorized. Okay? You will use it so often that you just memorize it. But if you want to double check, or if your mind just goes completely blank during a test, it's right there. So, this is a number called Avogadro's number. Avogadro's number. Sometimes we will write it like that. Okay? Avogadro's number. And there is a reason why it is that number. It's not just a randomly assigned number that we pick. If it was randomly assigned, we would pick a different number that was easier to work with. It actually comes from working with carbon. That is the number of carbon atoms in exactly 12 grams of carbon-12. Okay. Do you need to know that? No. Do you need to know that number? Yeah. So, Avogadro's number. And it really is just like any of these other things. If you have 1 mole of something, it is that many things. Yeah. Now, just to give you an idea of just how massive this number is, that is a huge, huge number. Okay? If we, for example, take a piece of paper. This is 1 sheet of paper. Let's say we have a mole worth of paper. And we stack them. Another one, and another one, and another one, until we have a mole worth of paper. Anyone want to guess how tall would that stack of paper be? We have a vote for the ceiling. Any other guesses? About there? Okay. No. In fact, if we had a mole of paper sheets stacked on each other, that pile would be approximately 6 times 10 to the 19th meters high. Whoa. There you go. So just to give you a little bit of reference as to what that distance means. Let's say we want to measure the distance from the Earth, I don't know, to the moon. The distance from the Earth to the moon is approximately 3.84 times 10 to the 8th. Okay, so obviously our stack is going to go past the moon. What about the sun? The distance to the sun is approximately 1.496 times 10 to the 10th. So now our stack of paper has gone past the sun. What about, well, I guess if we're already gone past the sun, let's go to the next closest star, Alpha Centauri, which is 4.2 light years away. But 4.2 light years is about 4.13 times 10 to the 13th meters.
What the heck? Maybe we set the left bit on the paper. If you needed that left bit in there.
Now, let's keep going. Does anyone know what the next closest galaxy is?
A galaxy?
The next closest galaxy. So we are in the Milky Way galaxy. Our next closest galactic neighbor is the Andromeda galaxy. Okay? Now, if you were to go outside in the darkest environment possible, there's no light pollution. Let's say you're out in the middle of the ocean, no lights anywhere. Okay? So you can see all of the stars. The Andromeda galaxy would look like a small smudge in the sky because it's that far away. But it is about 2.4 times 10 to the 19th meters away. So your stack of papers would stretch from Earth to the Andromeda galaxy and back, and then part way back. Okay? So we're starting to get a general idea of just how big this number is. Okay? And obviously, if we take anything else, for example, did the calculations for this. So if we stack them, these paper clips end to end, okay? If we had a mole's worth of paper clips, that would then be approximately 1.93 times 10 to the 22nd meter. So 3 orders of magnitude. Okay. Now, obviously, we can't just deal with going here to the next galaxy. Now, the entire diameter of the Milky Way galaxy is about 1 times 10 to the 21st meters. Okay. So a little bit of quick math. So that tells us if you had a mole's worth of paper clips, you could stretch back and forth across the Milky Way galaxy about 20 times. Okay. So yeah, this is a massive, massive number. Okay. So why do we need such a huge number? Why do we need such a huge number? Well, it's because atoms are really, really small. Remember, when we said the origins of that number, that was the number of atoms in 12 grams. Okay? So when we're dealing with normal amounts of stuff, if we need to know how many atoms or molecules or whatever there are, the numbers get really big really fast. Okay? And so that's why this number is so huge. Now, remember, this number works exactly the same as any of these other things that you're familiar with. So if you have 1 mole of neon atoms, how many atoms of neon do you have? Yeah, this many. 6.022 times 10 to the 23rd. If you have 1 mole of oxygen molecules, how many oxygen molecules do you have? 6.022 times 10 to the 23rd. Okay.
So every time, like every kind of something has the same number.
Anytime you're dealing with a mole, it is the same number. Okay. Anytime you're dealing with a mole. So if there's a question on the homework, hint, hint, there is, that asks how many atoms of, I can't remember which element it is, but it gives you an element, and it says how many atoms of this element are there in 1 mole? What's the answer? That right there. Okay. Now, what would you do if they said how many atoms are in 2 moles? Yeah, you take this and multiply it by 2. And that's your answer. Okay? Just like how we said how many eggs are in 2 dozen. You take how many you had, multiply it by how many units. Okay? It's the same thing.
So would you multiply the whole equation by 2?
Well, this is not an equation. It's scientific notation. It's a number. So remember, scientific notation, we're not actually performing this. It's just a number. So that's the mole. And we use it all the time in chemistry. We use it all the time. And that's why we want to really make sure you understand what we're talking about. Because this concept of what a mole is going to come back over and over and over. Okay? Now, we are going to be doing a lot of unit conversions in the next few days. Okay. And once again, these are pretty straightforward once you sort of get the pattern. Hopefully it makes sense as we go through this. But in order to convert between moles and particles, all we do is set up, now Saxon Math calls it a unit multiplier. Okay. The textbook calls it dimensional analysis. It's the same thing. Okay. So all we have to do is essentially multiply by 1. That's what dimensional analysis is. We're multiplying by 1. And that's what you were doing in your head already. So if we said we have 8 dozen eggs, and we wanted to know how many eggs are in 8 dozen. Well, really, what you did in your head was multiply by 1. And it may not seem like you did, but let me tell you why it was. Because what we multiplied by, let me set it up. Yeah, I'll show you that in just a bit. So 8 dozen eggs, and we multiplied it by a conversion factor. Because we know that we have 12 eggs in 1 dozen eggs. Okay? So 12 divided by 1 dozen is 1. Okay? When you're doing this dimensional analysis or unit multipliers, you can multiply by anything you want as long as they equal 1. Okay? As long as these two things, when you divide them out, equal 1, you can multiply by anything you want. Okay? It's a very, very powerful tool. We will use it all the time in chemistry. Okay? And if you notice, it's great because you can check your work by whether or not your units cancel out properly. So when we do this, so we have, remember this is above the fraction line. So if we have this above the fraction line and this below, they go away. Okay? And so the only unit we're left with is just eggs, which is what we wanted. So how many eggs are in 8 dozen? So all of these other units have gone away, and all we have to do is take 8 times 12 eggs, because all of the other units are gone, and we get 96 eggs. Okay? So that's what we're going to do. That is, honestly, so if you understand all that, you understand this unit. And all we have to do is apply it to the mole. Okay. So let's actually apply it to the mole. And this is where having a scientific calculator is going to help you. Okay. You will absolutely need a scientific calculator for the homework. Okay. If you don't have one, use one on your computer for now. But yeah. Up until now, you could have gotten by without having a calculator. For the rest of class, you're really going to want to have a calculator. And like I said, it doesn't have to be, a $100 calculator like I have. I love this calculator. But if you just have, you know, a $10 one like this, that works. Anyway, when we're going back and forth between moles and particles, our conversion factor is either going to be 6.022 times 10 to the 23rd particles. And we use particles on purpose because sometimes they're atoms and sometimes they're molecules. So we don't want to say atoms, we don't want to say molecules. To be completely correct and all-inclusive, we say particles. But anyway, that's just a minor thing that I'll point out. Over 1 mole. And a lot of times we leave off the E just because we're lazy, and that's what we do. Okay. So just so you know, most of the time when I write it on the board, it will just be MOL. That's the same thing. Okay. You'll also see it in the book written that way. It's just sort of the scientific consensus that we know what that means. Okay. So it'll either be this, or sometimes we have to flip it around. And do it this way. So these are going to be the two conversion factors that we have. Okay? If you are going from particles to moles or moles to particles, you'll use one of these. The only question is, which one do you use? Okay. Now I can tell you, going from moles to particles is the top one, and going from particles to moles is the bottom one. Now, if you want to just memorize that, you can, but it's a lot easier to see how the units are going to cancel out. So we'll do some examples so that we can show that. Okay. Now, it gives one example here, sucrose. Okay. So it says, basically, how many molecules, I mean, it says representative particles, in this case is molecules. So how many molecules of sucrose are in 3.5 moles? So whenever I have to do dimensional analysis, this is how I set it up. You get a line like this. Okay. And I just start with what I know, what the problem has given me. And in this case, 3.5, did it tell us 50? It did. 3.50 moles of sucrose. Now, I need to use one of these. Okay. And like I said, you can just memorize which one is which, but I find it easier to say, okay, I have moles right here on the top. I don't want moles in my final answer. I need to somehow get rid of that unit. Well, how do you get rid of a unit? You divide by the same unit, right? So that means I need to use this one because the mole on the bottom means it's going to cancel out and just leave me with the particles. So I'm going to pull this down. And in this case, we are dealing with molecules. In 1 mole. So the moles cancel out. We're left with molecules of sucrose. Okay. Now the reason why I write this line is because as we go through, we are going to have problems that are not solved in one step. We're going to need 2 or even more conversion factors. Okay? And the reason why I like this to do multiple conversion factors is because I can throw another one right there and do all of my math all at once. That minimizes rounding errors, and I just find it easier. Okay? But we'll get to that, and I'll show you examples of how that works. Once you get to the units that you want, the only thing you have to do is take all the numbers on the top and multiply them together. Then you take all the numbers on the bottom. So take all the numbers on top, multiply them together. All the numbers on the bottom, multiply them together. Take this number divided by that number, and that's your answer. Okay? So in this case, the bottom is really nice because it gives us 1. Every once in a while, we'll run into that where everything on the bottom is a 1. We really like it. It makes our job easier. Okay? But then we take 3.5, multiply it by Avogadro's number, and we get 2.11 times 10 to the 24. Okay. And then, of course, anything divided by 1 is just that number, so we can just get rid of that. And that's our answer. So in 3.5 moles of sucrose, there are 2.11 times 10 to the 24 molecules. Okay. Let's do another example. Let's look at, well, practice problems on 323. And we'll just do number 1. So zinc. It gives us some information about zinc. It's used to form a corrosion inhibiting surface on galvanized steel. Great. That doesn't help us in the problem. Determine the number of zinc atoms in 2.5 moles of zinc. So once again, we just start with what we know. And once again, we're going to pick our conversion factor. This one is going to be the same one because we need moles on the bottom. So we put Avogadro's number up here. This time we are dealing in atoms. Divided by 1 mole. Mole cancels out. We're left with atoms of zinc, which is exactly what we want. This one's another nice one because it's 1 on the bottom. So all we have to do is multiply 2.5 times Avogadro's number. We throw that into our calculator. Then get 1.51 times 10 to the 24 atoms of zinc. Okay. Make sense? Let's try one more. Okay. If we turn the page, we see a big example problem 1. We are now on page 324. We're going to deal with zinc again. Okay. Gives us some more information. It repeats the corrosion resistant coating. It's also an essential trace element in your diet. You need zinc. Okay. Calculate the number of moles of zinc that contain 4.5 times 10 to the 24th atoms. Okay. So now, a little bit different. But we still just start with what we know. Okay. We know 4.50 times 10 to the 24th atoms of zinc. Okay. Now, if we were to use this same conversion factor that we had used, the units would not cancel out. And after we did our multiplication, the units that we would be left with would be atoms squared over mole. And that makes no sense. But if we use this one, and say that there's 1 mole for every 6.022 times 10 to the 23rd atoms, okay? Now our atoms cancel out, and we're left with moles of zinc, which is what we want. Multiply across. Divide by what we have multiplied across here. That unit has been canceled out, so we don't bring it with.
7.47 times 10.
And we rounded off to 7.48.
Oh. Right.
Oh, well, that's probably because the book only used 1, 2. That's probably where the difference is.
Oh.
So yeah, put that second 2 in there, it's going to be a little bit smaller. So, on homework and tests and things, I understand some people will use 2, 2, and others will use just 2. The number's close enough that I can tell that you did it right. So, that being said, it's always a good idea to show your work because then I can really know for sure. Because if you set up this whole thing but hit a button wrong in your calculator, I can still see that you knew what you were doing and give you some credit. But if you hit a button wrong in your calculator and just give me the wrong number without showing any of your work, I don't know if you made a simple calculation error or if you did the whole thing wrong. So, always good to show your work. All right. Any questions about going back and forth between moles and particles? Okay. Well, honestly, that's the end of section 1. That's where we're going to stop for today. We will move on into.
Mr. White,
Yes,
could you send Wendy down to check out, please?
absolutely.
Thank you.
We will move on to mass and things. But for now, we're going to stop at section 1, and I'll let you start on some homework. So. So that is at the end of chapter 10, and I will give you like 20 minutes left in class or so. Honestly, you could probably finish this in 20 minutes because mostly it's doing this.